So if we want the adder to do subtraction, we need to add a 2's complement portion, and that 2's complement needs to apply to a mux, which then goes into the adder for the second value. So this is very important. It's the only way that you can do subtraction that I know of in an adder. Otherwise, you can just use an adder if you're not worried about subtraction. So let's talk about our shifter block diagram. So a shifter is essentially going to move the bit left or right, and that's shown as we have two inputs: input 32 bits A, input 32 bits B, output 32 bits, which is going to be a left shift, or output 32 bits for the right shift. Scrolling down, we have the ALU. So this isn't the one I want to look at. This is the one I want to look at. So this is our level 1 block diagram for the ALU. It has addition, it has subtraction with the 2's bit, and it has the various functions for XOR, AND, OR, NOR. It has an adder, a shift register. It also shows the values of the output values of the various operations and the inputs of an 8 to 1 mux. And the 8th input is a 30-bit number equal to 0. This block diagram is also going to show the output of the mux, which is the output value of one of the operations, and it is the output of the ALU. So going up to this one up here, it's just a more simplified version. These are all the functions we can complete: 32-bit input A, 32-bit input B, 1 input C in. We need our opcode, of course. These are the various different things we need to solve for, which is the overflow for V, the Z for 0, the N for negative, and the carry out, which is C or C out. And these are going to be a 4-bit output that comes out. So now let's look at our results. So, we have all of our test benches for the various different parts. I'm not going to go through these step by step, but you can see the results. Then we want to get to the ALU. Just give me one moment. So the ALU, I believe I'm looking at the right one. So hold on. The ALU is going to use an 8 to 1 mux to select which of the operations in the ALU we're going to do. Are we going to do XOR, AND, OR, NOR? Are we going to add? Are we going to subtract? Are we going to shift to left? Are we going to shift to right? This is important and something that our code is going to use. The ALU has the status values, which is the carry out, which is C out, of the input of the adder / subtractor. It has the overflow V, which becomes 1 if the sign bit of the inputs of the adder / subtractor are the same number. And it has Z for 0, which becomes 1 if the output number of the ALU is 0. And we have N for negative, which is the status when the value becomes 1 if the sign bit is obviously negative of the output. So in this simulation, it goes through all the operations with 3 different pairs of values for A and B. The first pair of the values is shown above this. I guess I can scroll up to show. It's a lot of numbers to say. As you can see, A equals, you can see my mouse right here. These are the first inputs. Then we have our second inputs. And we can see the results that we're going to expect. So this is the first inputs version, the first inputs test bench. So looking at the first inputs test bench, we have the ALU code, the ALU input for input 1, 32 bits. We have the input 2, 32 bits. We have our CIN value, which is 0. We have our select value, which is 3 bits. We have our output value, which is shown right here, and then we have all different 32-bit values going all the way down from 0 to 31. And then we have the status right down here. And these are the results for the first inputs, which show that our ALU successfully works. If you go down here, it has values for the second test bench that I showed previously: 32-bit input A, 32-bit input B, CIN of 0, 3-bit select. We have all 32 bits, and our output 32 bits right there. And our status. Again, as you can see, even with different variables, it successfully